Hi, my name is Ahmet Coksaygili, and this is my Project 2 presentation based on forging, submitted to Mr. Hassan Rashidi for 3210. All of the sources required will be provided in the slides. What is forging? Forging, in general, is basically utilization of plastic deformation to get to an end product or an end shape. What are the advantages of forging? It has superior mechanical properties to most manufacturing methods. It reduces manufacturing time compared to traditional manufacturing methods, as you basically get to the end shape. It reduces scrap or has no scrap. It reduces energy consumption as it has no scrap. And one of the main reasons you have energy is the material acquisition itself. And it has the ability to change material crystal or phase structure during manufacturing. What are the applications of forging? Any ductile material with non-amorphous grain structure can be forged. This is mostly metals and some ceramics. Extremely experimental right now though. And forging is mostly utilized when there's a need for a high strength, high volume, and low cost production of parts. One of the main examples of forging is piston rods or piston heads, where they are very high strength materials for a pretty low cost. Engine cranks, turbine blades, and gears, especially gear blanks, are also usually forged. What are the goals of forging? There are three general goals in forging. Getting to the closest shape or to end product is the main goal of all manufacturing processes. It is very self-explanatory. Getting grains of the material aligned with the force stress on the material is very uncommon, and it is basically the main reason why we forge stuff. As we can see in here, if you cast something, the grain structure is very unaligned, so you have incredible amounts of grain breaks, and those grain breaks basically allow you to have crack formation or crack propagation at those points. If you machine something, the machining itself cuts into those grain lines, again resulting in points where crack formation or crack propagation can happen. If you forge something though, the grains will flow with the material's outline and material's basically stress flow, which results in less grain breaks and less crack propagation or crack formation at said grain breaks. This is especially important with high fatigue loads, as most crack propagation happens in those cases. Another advantage of forging is changing the phase and grain structure of the materials. So we go with a perlite material and we want to start an authentic material. We can forge at a higher temperature. We can get the material property we want, and we can quench at that point to get the material property that we need. Also, the recrystallization allows us to go for finer or rougher grain sizes, which is again an engineering parameter that we want to utilize to get better products. What are the forging methodology that is used in the industry right now? It can be dependent on basically three factors. It can be based on temperature, based on die geometry, or based on force application. With temperature, we have hot, warm, cold, and isothermal forging. Hot basically means that we are above recrystallization, warm means we are at recrystallization, cold means we are below recrystallization. Isothermal means that is not about the material itself, but the die temperature. For all of these processes, as hotter you go, you have finer grain sizes, less strength, but more ductility. And lower you go, you have more strength, less ductility, and coarser grains. And also the forging forces increase colder you go. Based on die geometry, open die, closed die. Very simple. Open die results in very cheap to manufacture dies with low precision, and you need to have a lot of post-processing. Closed die, you can go very complex dies, which is costly, especially for singular runs, but you do not need to do that much post-processing. Based on force application, kinetic or static. Static or presses allow you to have better deformation control and better force control, while kinetic application allows you to have higher final impact forces. So harder to process materials are usually done kinetically. What are the skill sets needed in the forging industry? There are basically four main skill sets needed in the forging industry, especially as an operator or equipment designer. You have to have a very good understanding of material behavior and plasticity. Methods such as slab method and plasticity models such as Johnson, Cook, Holloman, or Swift really requires you to understand which the material properties you're working with, which material conditions you're working with, and how those are going to be applied to your final product. Another thing you have to be understanding is reading phase diagrams, understanding grain structures, grain propagation, and this kind of material science parts of the forging process, as your main and end product is basically dependent on those properties and on those phenomena. Another thing that is very important right now, especially in the forging industry, is understanding of heat transfer. Heat transfer between die and material, and also heat transfer in actual heating processes. Industry is very much inclined to go towards induction heating rather than conventional heating methods, which requires you to understand heat transfer to get a consistent thermal profile across your material, as induction heating basically generates heat on the material itself rather than just heating up to a certain ambient temperature. Two other skill sets you really need in the forging industry right now is understanding of empirical model and reverse data analysis. So in general, while we are doing forging, stuff such as your friction factors are determined based on experiments and empirical models based on those experiments and data analysis of those experiments, empirical models. So you have to be really competent at designing experiments, understanding said experiments, and doing data analysis and empirical models on said experiments to be competent as a forging engineer. Another thing is you have to understand FEA, especially with complex dies in modern working conditions and modern research, such as what I am doing right now in my forging lab. You have to be understanding of which FEA models to go for, explicit or implicit, based on force application basically. Implicit really works well with presses, and explicit works really well with hammers. Or what you should do with your plastic deformation. You should go reduced or unreduced. How you are going to rein in plastic deformation, or how you're going to rein in hourglassing. All of these things require you to have understanding of all of the skill sets we talked about before, and also understanding how the FEA systems work themselves individually. So what are the future trends and innovation in forging in general? One of the main ones is metaforming manufacturing. Metaforming manufacturing is the idea that we can use sensors, thermal control, actuators, and forming tools, robotic manipulation, and computation. All of these to create incrementally forged parts with different properties at different parts of the part. The idea with metaphoric manufacturing in general is you have a very specific end shape that you want to go for with very specific material properties at very specific points, and you are controlling every little stroke based on that. So this is the main goal of most of the forging research right now in the industry. Other future trends and innovations in forging is flashless forging. Flashless forging is, especially with closed die forging, is the process of forging with no flash or scrap on the forged material itself. It reduces post-machining time immensely, and it is very favorable for manufacturing. However, it requires immense amounts of engineering time, FEA work, and also it requires very precise dies. So right now, it is very much mitigated to only high volume, high value productions. However, especially with how the industry is trying to innovate and trend towards there, a lot of the low volume productions, I think, are going to be also in flashless producing, and that's what the industry magazines mostly talk about as well. Another thing is scaling, reduction, and mitigation. Scaling happens when oxidation happens in forging processes, especially with open die forging, and it is bad for you because it reduces material strength and it messes with your material properties. So coatings or vacuum processes to get rid of scaling or mitigate scaling has been very popular research topics in the last couple of years. Crystal plasticity has also been very research popular. Anisotropy or lack of anisotropy is a very important thing in forging. We can create, especially with modeling and understanding crystal plasticity, anisotropic material properties with forged materials. So you can have very high strength in one direction and very low strength in another direction. And the modeling of crystal plasticity in the last couple of years and utilization of that in forging has been actually very popular. That's what my professor in my forging lab works on, and it's been quite an interesting topic to work with him. In situ forging, another very interesting topic right now going on in the forging industry, where you forge the material you want to forge while you're also machining it in the same space. This allows you to do very complex geometries in a small time frame, and also allows you to do achieve anisotropy through incremental forging or small forged parts getting machined at certain points to change material properties. And all of these meshing of the normal commercial manufacturing and forging is really being beneficial for the industry. Lastly, constitutive AI models has been very popular as well, where forging usually requires high amounts of FEA work, especially for complex dies. But we can train AI on simpler FEA models and get AI predictions on how the complex dies are actually going to behave. And based on that, we can get rid of a lot of the FEA work that we need to have very fast manufacturing. Thanks for listening to me. I hope you enjoyed my presentation, and I wish you a very good day.